We're gonna learn what symbolic execution is and how to use it. But first, let's play a game. We're gonna play a roguelite dungeon crawler game. So we start by picking a character and some starting equipment. We have some gems and a scroll with some incantations written on it. We enter the first room of the dungeon. The way the game works is that some rooms contain a challenge, and based on the outcome of the challenge, we can open either the first door or the second door. In the first room, in order to open the first door, we need to have at least some gems, and in order to open the second door, we need to have no gems. Because we had some gems in our starting equipment, we get to open the first door. So we open it, and we find ourselves in a trapped room. So we lose a life, and that ends our first run. Luckily, we have infinite lives and we get to play again. This time, we know we don't want to take this door, we want to take the door at the bottom, so we take no gems. This allows us to open the door at the bottom and enter the next room. This room contains a piggy bank. The way the challenge works is that we need to scribble a number on our scroll. If that number is larger than the amount in the piggy bank, we get to open the door on the right, otherwise we open the door at the bottom. For now, let's assume that we wrote a larger number, so we open the door on the right. Unfortunately, that's another trapped room, so we lose another life and start a new run. So this time we know that we want to go down and then down again. So we take no gems and write a smaller number on the scroll. This new room contains a challenge based on the name of our character. You get the idea. We're going to keep playing, opening all the doors we can and mapping out the entire dungeon, solving challenges one at a time. Eventually, we've mapped out the entire dungeon and we find the room with the final boss. The final boss is a dragon with a riddle for us. In order to solve the level successfully, we need to solve the riddle. It may become clear at this point that we haven't really been playing a weird game. Believe it or not, what we've been doing is that we've been symbolically executing the transfer from function of the with9 contract. What do I mean by this? If you take the control flow graph of that transfer from function, it looks like this. The shape should feel familiar at this point. Each room with two doors corresponds to a branching condition. To see how it corresponds to our example, consider the first room where we check the number of gems we had. In the transfer from function, it corresponds to the call value check. Because it's a non-payable function, if we have a non-zero call value, then we revert right away. This corresponds to the first trapped room. And you can see the correspondence like this for each test. In fact, every abstract symbol we've used in our game corresponds to some input value or some state of the contract. The character was the message sender, the gems were the message value, the scroll corresponds to the message data, and we also had the piggy bank corresponding to the balance, the allowance, and so on. For the final boss, the dragon, I'll explain a little bit later what it corresponds to. This brings us to our first takeaway. You now know what symbolic execution is. We have some inputs and some initial state that correspond to our starting equipment and the contents of the dungeon. And of course, we have one or more dragons to defeat. This is our target. We solve challenges in order to open doors and keep track of the conditions necessary to get there. We do this until we've found and defeated a dragon, or we run out of rooms to explore. Now that you understand the process of symbolic execution, you can already foresee some difficulties we may run into. Like in a video game, some levels may be fairly easy, and some levels may be impossibly hard. For instance, the dungeon could have multiple floors and be huge. In fact, it can even be infinite. If you have heard of the term path explosion, this is what it refers to. The program you want to analyze has some intrinsic complexity that makes it difficult to process for any tool, not just symbolic execution. And even when you have a limited number of paths to deal with, some paths can be trivial to explore, some paths can be impossible to explore, and in some cases, it may be very hard to determine exactly the right set of inputs that would let you go down a certain path. Now that we know what symbolic execution is, we're going to see how to use it. Let's say that we want to test the transfer from function. There are a number of properties that we might want to test for. For instance, transferring from source to destination should never change the total supply. It should also decrease the balance of the source by exactly the right amount and increase the balance of the destination by exactly the right amount. It should also not change the balance of anybody else. Let's consider this test for that final property, that no other balance is impacted by a transfer. We have a GUI address, a source address, and a destination address, an amount called WAD, and a GAL address. We start by assuming that the GAL address is distinct from the destination and the source. We then take a snapshot of the starting balance of that GAL address. Then the GUI address invokes the transfer from function. Finally, we assert that the balance of the GAL address has been unchanged by the transfer from function. A test like this probably looks familiar, and you may think of it as a fuzzing test. But in fact, I would argue that it's more general than a fuzzing test. It's actually a property test. If you run that property test with a fuzzer, then it will be executed with random inputs. But if you run that property test with a symbolic testing tool, instead of random concrete inputs, it will use symbolic values to explore all possible paths in that program and check the assertion. Let's take a look and see what this looks like. If we go back to our starting dungeon analogy, this test is setting up the dungeon in a particular configuration. Let's assume that the starting state of our contract is initialized in the setup function, but no particular addresses have any either balances or allowances, so these mappings are empty for now. Because we invoke the transfer from function from the GUI address, this corresponds to our character, and because we don't specify a value, we have no gems. Our message data corresponding to the contents of the scroll is the ABI encoding of the transfer from call, and the actual dungeon itself is the code of the transfer from function. We now see what the final boss corresponds to. It corresponds to the assert at the end. This is the target of our test. We're going to use symbolic execution to explore all possible paths in the transfer from function and look for a path that leads to an assertion failure, aka defeat the dragon. Let's take a look at our first path. Because our call value is 0, we take the second door to go down, and then we have a check against the WAD amount. Let's assume that WAD is greater than 0. Because our balance mapping is empty, that causes a revert. We reached the end of a path, so we check our assertion. Because of the revert, no state has changed, so our assertion check passes. But we're not done yet. Let's consider a second path, where this time we consider that WAD is 0. We now have a second test where we compare source against the message sender, in our case GUI. Let's assume that source is GUI. So we go down, fail that second check, and then proceed to updating the balances. Even though WAD is 0, the balances are still updated in storage and the transfer event is still emitted. We reached the end of our second path, so we check our assertion. No balances have actually changed because the WAD amount is 0, so again, the assertion check passes. We still have more work to do. Let's assume this time that source is different from GUI. This corresponds to a third-party transfer from. Because our allowance mapping is empty, the allowance is 0, and therefore it is not unit max. So that second test passes, and we now go down the path where we decrease the allowance by the amount of WAD, which is still 0, and then proceed to updating the balances and emitting the transfers. We reach the end of our third path, and again the assertion check passes. We have explored every feasible path given our starting assumptions, and across every path, our assertion checks out. Therefore, our test passes. This is an important takeaway. This is what it means for symbolic test to pass. Symbolic testing means that we're going to use symbolic execution to check an assertion over all reachable paths for a particular program and set of symbolic inputs. You should note that there is a fundamental difference with fuzzing here. With symbolic testing, a test passing is meaningful and definitive. You can run it every time and you will always get the same result, because we've systematically explored every path and found no possible assertion failure. With fuzzing, a pass is by definition incomplete. It means you ran out of fuzzing budget, but you could in theory fuzz forever in the hope of maybe finding something. If the program you're fuzzing does not actually contain a violation of your assertion, then you are doomed to fuzz forever. Let's now look at how we can improve our symbolic test. Our symbolic test passes with significant coverage. If we look at all the paths we cover, almost every condition and branch has been taken. However, it does not feel very satisfying because, as we saw when we ran it manually, we only consider null transfers. We also don't consider the case where the mappings are initialized to some values, so people having balances and allowances. Let's fix that. We can make our test more general by adding two new arguments, balance of source and allowance. We also add some code to mint some wrapped ether to the source address and to set up some allowance between source and guy. Note that in the context of a symbolic test, these values are still fully symbolic, so they could have arbitrary values, including 0, like before, or any other value. This means that running symbolic execution with these new assumptions opens up new paths that are feasible now. In particular, we have a new revert path in the case where the allowance is insufficient. And we also have the case of a third-party transfer with allowance set to uint max. Our new test is a lot more expressive. It covers a lot more use cases that feel more natural, and they properly exercise the logic of the function. It translates to a better coverage, more path, and in this case, an assertion that still holds along every path we explore. So our test still passes. This should come as good news. I'm not here to reveal an invariant violation in the with9 transfer from function. However, our property test does not hold for every ERC20 out there. In particular, it does not hold for tokens that implement a fee on transfer. If we take a look at this transfer from function, it has roughly the same shape as the transfer from function of the with9 contract. But there is that extra line that increments the balance of the fee recipient by some static fee in this case. If you run a symbolic testing tool against such a token, it should be able to report a violation of the assertion. Our test is asking, is it true that no other balance other than source and destination are changed by a transfer from? And the tool responds, no, it's not true. There is a fee recipient address that is changed. This is another important takeaway. You should never trust a test that has never failed. Because we now have a valid counterexample for this property test, we can be more confident that it properly works. It does what it says on the tin. To recap, the way you can leverage symbolic execution is by using a symbolic testing tool. What this typically means is that you focus on writing good property tests in Solidity with expressive preconditions and meaningful assertions. Symbolic testing tools will then translate the semantics of your tests and your contracts into an intermediate form like an SMT formula, and it will then query a solver to play the dungeon game for you. Specifically, it will query the solver to know if a certain path is feasible or not, and if there are certain inputs that can lead to an assertion violation. If the solver reports a violation, it will report the inputs that lead to the violation, and mark your test as failed, just like a fuzzer would. Speaking of fuzzing, let's take a deeper look at how it relates to symbolic testing. Suppose that you wrote a test and you have a bug that is fairly simple to find. Let's say that you have 1 chance in a million to hit the bug with some random input. A fuzzer is very likely to find and report this bug very quickly, because that's what they're best at, and a million runs are cheap to execute even on a laptop. Symbolic testing tools may be able to find it, but they are likely to be slower. Why? Because of the overhead of SMT modeling and querying an external solver. Additionally, some queries like those involving nonlinear arithmetic are fundamentally hard for solvers to reason about, and so randomized testing is likely your best bet here. Now let's focus on the case where there is no test failure to be found. That is the transfer from example we have been working with, and as you've seen, symbolic testing can rule out assertion violations. How long it takes to do so depends heavily on the complexity of the program and the assertion, but in the case of transfer from, you can expect very fast results. On the other hand, this is the absolute worst case for a fuzzer. There are no successful fuzzing tests, only timeout, and this is the best you can hope for here. Finally, let's focus on the case where we have a complex bug hiding. By complex, I mean that you have a very small chance to find the bug randomly. Think less than 1 in a trillion. So it's still possible to find, but it is now considerably more expensive to run. This is arguably the worst case because you can't expect an answer in a reasonable time with either fuzzing or symbolic testing. Think weeks instead of seconds. And of course, the real problem is that you don't actually know where you fall on the map. Ideally, you want to make sure you either have simple bugs or no bugs at all. But in practice, a complex bug and no bug look a lot alike. You just get fuzzer timeouts. In order to raise your confidence level that you don't have a complex bug, a pragmatic approach is to root out simple bugs with fuzzing, find cases where you have no bugs with symbolic testing, and then try your best to break down functions where complex bugs may be hiding. And finally, you can throw as much compute as you can afford on trying to fuzz and test symbolically for complex bugs. This brings us to the end of our symbolic journey. You should now have a solid intuition for what symbolic execution is and how it's leveraged for you by symbolic testing tools. I have a couple good news for you. If you know how to write Foundry-style fuzzing tests, you already know how to write symbolic tests. Additionally, there are a number of open source testing tools that you can use today on your own codebase. This includes the tool I personally work on at A16Z called Halmos. Because we're open source, we welcome your feedback and your contributions. The final and most important point I want to leave you with is that if you write property tests in Solidity, you have both fuzzing and symbolic testing available to you. You now understand that these tools work fundamentally differently and they have different strengths that complement each other. Fuzzing can be very effective at finding bugs quickly, especially in math-heavy sections of the code. On the other hand, symbolic testing tools have the potential to completely cover all feasible paths in your contract, and tell you definitively when no assertion violation can be found. This lets you save your CPU cycles for fuzzing more complex functions and not these type of tests.
Okay, awesome. Thank you so much for being here, even for our remote talk. And let's please have a huge round of applause, even though Daniel could not join us.